If you have not watched Katie's video, go back and watch it and then start this one after. All right. Continuing with Katie's story, Katie was talking about methane bubbling up through lakes in the Arctic. Well, this last year, there's been some even crazier stuff. Over in Siberia, which as you know is mostly permafrost, they have been discovering these giant craters. Now, if these craters were due to asteroids, we would have some record of the asteroids coming, hitting the Earth because they just happened recently. They look like the result of giant explosions. And so people have been suspecting, if you can read the caption there at the bottom, people have attributed these to meteorite impacts, missile strikes, gas field explosions, but the likeliest explanation is the buildup of methane underground from thawing permafrost, and then because it is natural gas, it is exploding under pressure. That is pretty crazy. Here is another video for you to go watch. I know this is easier to do in class, but what I want you to do now is pause this video. You should know how to do it by now, right? Pause this video and go watch this one, which is a Russian scientist actually standing in front of one of those craters telling you about it. It is crazy to see it with your own eyes. Okay, so stop this video and go watch it right now. All right, you should have just finished the video of the Russian scientist standing in front of the giant crater in Siberia. And now we're going to go back to talking about these climate feedbacks. Why does it matter how sensitive the planet is? It matters because that tells us how much temperature is going to change for a given scenario. Do you remember back about 15 minutes or so ago, we talked about all the different scenarios of carbon emissions from human activities that we look at? So this shows not carbon emissions. This figure shows global temperature change in degrees Fahrenheit for the higher scenario and for the lower scenario. The dark line is assuming climate sensitivity is 3 degrees Celsius, which is the average value, but the shaded area shows what would happen if it were less or if it were greater than the average value. That's why climate sensitivity matters, because for a given scenario, it's going to give us even more temperature change if it's higher, and it's going to give us less temperature change if it's lower, which is what we want. So we've talked through natural, we've talked through human, we've talked through the first type of scientific uncertainty. Now we're on the last one. Climate models aren't perfect. Big surprise. Climate models try to take the entire climate system, the sun, clouds, volcanoes, snow and ice, biosphere, humans, ocean, atmosphere, land surface. They try to take the entire climate system and put it into a computer. As you can imagine, this is not an easy task. And that's why computer models are some of the longest and most complex and most time-consuming types of computer code that exist on the entire planet. This is, again, literally a simple diagram of a climate model. And again, this simple diagram, so to speak, will not be on the quiz. But I show it to you because I want you to see how much physics is in a climate model. This is all physics. This is not statistical correlations between CO2 and temperature. This is literally measuring the different types of energy that are exchanged within the climate system. This is pretty crazy. Just look at this for a minute. Look at everything that is in this. So here's your third discussion question. Again, remember, I just want you to answer 3 out of the 4. Number 4 will be coming up. And I'm looking for short answers. I'm not looking for big pages. I'm just looking for a few sentences. So here's question number 3. Why use climate models? And what do you think is the biggest benefit of using them? What do you think is the biggest drawback to using them? Think about that as we talk about climate models here. So how do we experiment with the planet? Whenever I get a reporter coming to interview me with a TV camera, they always want to interview me in my lab. And I guess they're picturing, labs with equipment and fume hoods and experiments. But the reality is I experiment with the planet. And the way I experiment with the planet is by building a computer model of the planet. So we put our computer model, we can't put it into a test tube. We don't have any equipment. The people who come with their video cameras are always disappointed because I show them my computer and I say, this is my lab, and I connect my computer to the high performance computing center on campus. And if you want a picture of me walking up and down through rows of black boxes, you can, but those black boxes, those are all the different servers at the high performance computing center. Those black boxes are my lab because that's where I run experiments with the planet. So our lab are these big supercomputers where we turn the climate system into thousands of lines of code. And this is just an example of what a few dozen of those lines look like. Again, these lines will not be on the quiz. But the whole point is, this is what a climate model looks like. Pretty crazy, isn't it? Now, this is a picture of the computers that some of my colleagues used at the Geophysical Fluid Dynamics lab in Princeton. They were so sick of having reporters come and ask to see their lab and then being disappointed by their lab that they actually just put this picture on their computers so that reporters would have something to actually take a picture of. As you can see, it looks pretty. But this is their lab. What are climate models? Climate models take the Earth, including the atmosphere, the land surface, and the ocean, and they divide it up into finer and finer grids, little grid boxes. The higher powered the computer we run on, the more grid boxes we can use. Using these grids, we can model the circulation of the atmosphere. In fact, the amazing thing is the very first global climate model or general circulation model that didn't just look at energy fluxes like Arrhenius did back in 1890, but actually looked at the circulation of the atmosphere, the very first model was a physics experiment. If you solve the equations of nonlinear fluid dynamics for the specific case of a fluid, that's the atmosphere, on a rotating sphere, could you get the circulation systems we see in the atmosphere? They did this back at GFDL, that place I just showed you a picture of, on a much older computer back in the 1950s, and it turns out you can. The circulation patterns in the atmosphere are simply nonlinear fluid dynamics. It's really amazing. The circulation of the atmosphere is mainly the result of the fact that we get more sunlight at the tropics than we do at the poles because of the way that the Earth is tilted. And the atmosphere is just trying to constantly restore the balance. It's always constantly trying to push more energy up to the poles. That's why we have atmospheric circulation. The idea that you could model the circulation of the atmosphere, the winds, the jet stream, the Hadley cell, the idea that you could do this actually came from, I'm sure this will not surprise you at this point, it came from a scientist in the early 1900s called Wilhelm Bjerknes. And this is literally what he said. These are his words. If it is true, as every scientist believes, now again, we're talking about scientists over 100 years ago. If it is true, as every scientist believes, that subsequent atmospheric states, weather patterns, developed from the preceding ones according to physical law, then it is apparent that the necessary and sufficient conditions for the rational solution of forecasting, because these are weather models too. Weather models and climate models are both based on physics. You just need a sufficiently accurate knowledge of the initial conditions and a sufficiently accurate knowledge of the laws according to which one state of the atmosphere develops from another. Pretty amazing, eh? What type of physics are in climate models? Climate models are based on 6 first principles of physics: conservation of momentum and energy and mass and moisture, equation of state that relates pressure, temperature, and density, and the hydrostatic equation, how temperature and pressure vary with height. Climate models are basic physics. This is what it looks like. And again, you don't have to worry about this. This will not be on the quiz. You won't have to come up with these differential equations. But I think it's pretty cool that in order to describe the atmosphere in every single little box around the whole planet, these are the only equations we need, and we only need 7 unknown factors. U and V, if you look at the very bottom, U and V are the winds in the horizontal direction, north, south, and east, west. W is the wind in the vertical direction, or the movement of air vertically up or down. T is, of course, temperature. Q is moisture. And then we also have density and pressure. That's it. So how does this all work? Picture a Rubik's Cube. I don't know if anybody was watching America's Got Talent this summer, but they had this guy who could do amazing things with Rubik's Cubes. I think we've all probably tried a Rubik's Cube once or twice in our life. So picture a climate model as a Rubik's Cube where you divide the atmosphere and the ocean and the land surface up into these little grids. So let's look at this little grid right here. Every time step, we look at what the temperature is in that grid. How does the model calculate how the temperature is going up or down? We look at the energy that's going into the box from the sun. We look at the energy that's going in that's reflected from other boxes into that box, maybe off clouds or particles. Then we look at the heat that's going in from other boxes and the heat that's going out from that box. We also look at whether there's condensation occurring or evaporation, because changes of state for water also take away or contribute heat. And then we add all of that together and we figure out what's the temperature at the next time step. We do all of these calculations at every single grid box in the whole climate system. We update it all and then we move on to the next step. You can see why this takes a very long time. It takes about 2 to 3 months to run 100 years of simulations. That's a very long time. So you probably remember the ozone hole, and you remember that there was chemicals in our spray cans and in our air conditioners, and actually even in our Nike Air shoes. Chemicals that were entirely made by people. In other words, they don't occur naturally. These chemicals are CFCs, or chlorofluorocarbons. So because we produce these CFCs from humans, not naturally, and because they last a very long time, they have lifetimes on the order of thousands of years, we can trace how these chemicals move through the ocean and the atmosphere to see what the circulation or the transport patterns look like in the ocean and the atmosphere. So up top, you have the observed patterns of CFC11. There's a couple of different ones, but this is the main one. CFC11 from our spray cans and our air conditioners. You see where it's gone in the ocean over the last 30 years or so since we were producing it. We don't produce it anymore. Thankfully, we stopped, and we've replaced it with other compounds, but because it lasts so long, it's still here. Now on the bottom, you see the output from the climate model. Where would it put the CFC if it had it coming out of spray cans all over the world? You can see again, it's pretty close. Not perfect, but pretty close. So this gives us kind of an independent test of how well this model is able to reproduce the circulation of the atmosphere and the ocean. If you produce all of these CFCs from spray cans, where do they go? It puts them in the right place. We also use these models to look forward into the future. What would happen if we could flip a magic switch and turn off all our carbon emissions today? We would still see some amount of warming. That's the bottom panel. What would happen if we could significantly reduce our emissions? That's the top panel, a medium to low scenario. This is the temperature change in degrees Celsius. As you can see, there's regional patterns. It's warmer over land, and it's much warmer up in the Arctic. And of course, we just talked about why it would be warmer up in the Arctic, right? Do you remember? Climate models get more complicated over time. This is a figure I actually just made myself. Back in the times of Arrhenius, climate models were just looking at the transfer of energy. That's it. Then in the 1950s at GFDL, they added nonlinear fluid dynamics, or circulation. The next thing to be added was the hydrological cycle, water. Then they added sea ice and land surface. Then they added aerosols. Now aerosols are not spray cans here. Aerosols are dust and soot particles and chemistry. And then the most recent thing they're adding are biogeochemical cycles like carbon and nitrogen. The models are also increasing in their resolution over time. Look at what they used to look like back in 1990. You can barely even recognize what you're looking at, right? But by the time you get down to 2005, I think everybody realizes what you're looking at. And today we even have models where the grid cells aren't just 100 kilometers per side, they're actually 25 kilometers per side. So the more powerful our computers, the better and better the resolution we can use on our climate models. It's still a lot of it the same physics, it's just better resolution. This is another way to look at the resolution. This is the GFDL climate model, the one I was talking about before, the one I showed you the picture of, where they put a picture over their computers so people could see something pretty when they asked for the lab. This is the GFDL climate model back in the 1980s. Look at the Caribbean. The grid cells aren't even connected to each other. And look at the ocean over there. I mean, you can see patterns of warmer in the tropics to cooler up in the Arctic, but you can't see any eddies or pools or circulation patterns. Fast forward to 2009, and this is what the model looks like that they're using. Look at the Caribbean, it looks completely different. It looks like a map, doesn't it? And look at the ocean. Isn't that amazing? You see those eddies there? That is entirely physics. Nobody told the model to produce those eddies. You just put in nonlinear fluid dynamics, and that is what comes out the other end. It's pretty amazing. Why are climate models uncertain? They're uncertain for two main reasons. The first is structural uncertainty, and the second is parametric uncertainty. Now, these are some big words, but they mean pretty simple concepts. Structural uncertainty means, do we have everything in the model that we're supposed to have? Is anything missing, or is anything in the model represented incorrectly? Parametric uncertainty is different. How do we represent processes that occur at spatial scales or at temporal scales that are smaller than the model can resolve? So remember I told you that the highest resolution GFDL model right now, each little box, each little grid cell is 25 kilometers per side. So that's about, 15 miles per side. That's pretty high resolution when you think of dividing the entire globe up into little boxes. But what spatial scale does precipitation occur over? Remember we talked about that about half an hour ago. Precipitation occurs over scales about this big. A cloud drop or a raindrop or a snowflake. So how do we represent the behavior of millions of water droplets or millions of cloud particles or millions of snowflakes in a climate model that has a box that's 25 kilometers per side? That's parametric uncertainty. So structural uncertainty, again, are processes that we have in the model, but we don't know if it's right, or we don't know if we're doing it correctly, or processes that we don't have in the model, like the possibility of surprise. And I'll give you one terrible example of structural uncertainty. You know how we just talked about the methane leaking out of the permafrost in the Arctic? Do we know it's happening? Yes, we can measure it. Do we know how fast it's happening? Well, we know that it's accelerated over the past 10 years. But we don't know exactly how it's going to change in the future. We know it's going to keep on going for sure, but is it going to be medium-sized or is it going to be huge? Because it's uncertain, we haven't even put it in the climate models yet. So the climate models don't even have the methane from the Arctic in them. That's a huge structural uncertainty. Now I want you to think about this. If climate models do not account for the methane leaking in the Arctic, are the models biased too high or too low? Will they give us temperature projections that are too high or too low? If you said too high, you're wrong. Too low is the right answer. Because if you add all that extra methane, it is going to bump the temperature up even more. I told you it keeps me up at night. All right, parametrizations. These are processes that we can't explicitly model. Stuff that can't be modeled directly because it's occurring at scales that are too small. And again, rain, cloud particles are some of the best examples. But I'm sure there's many more. So here's your last discussion question. And again, remember, send me answers to only 3 of these. Don't have to do 4. And I'm only looking for a few sentences for each. I'm not looking for a big paragraph and certainly not a page of answers for each question, please. Last question. What type of basic science do you think is relevant to climate modeling? Give one example of a structural uncertainty and one example of a parametric uncertainty that I haven't mentioned already. Tricky, I know. What's the bottom line on climate models? Our models are getting better over time, especially as the resolution increases. There isn't a perfect or a best model, but they can definitely be pretty useful because what other choice do we have when we're looking into the future, right? Understanding their limitations and their uncertainties are really important to understanding what comes out the other end. And the bottom line is if you ever have to work with climate models, try to use as many as you can, because using what you call a multi-model ensemble, that's like a lot of different climate models together, using a lot of different models together is usually closer to reality than trying to pick a single climate model that's the best. So just to review, why are future projections uncertain? They're uncertain because natural variability is chaotic, so we have to make sure we look over sufficiently long time scales when we look to the future as well as when we look at trends in the past, both. Future scenarios are driven by human activities, right? So we have to make some assumptions regarding population, demographics, technology, and especially energy use. Our climate sensitivity is unknown. We think it's around 3 degrees for a doubling of CO2, but you know what? It could be lower and it definitely could be higher. And of course, our climate models are not perfect. This shows, for example, projected changes in rainfall or precipitation over Texas. Depending on whether you use good models, okay models, or bad models, or whether you use all the models together, sometimes you can get a different answer. And what you're looking at here is what I spend about 1/3 of my time on. I spend a ton of time kicking the tires on climate models. So here are your discussion questions again. And remember, you had a first set of discussion questions about the skeptical science articles at the beginning of video number 1. And then in 2 weeks, I know we're going to have the quiz. So just a few reminders. The quiz is closed book. If you want to type your answers, you can, but I'm going to ask you to make sure your internet is turned off and to make sure that your screen is placed to where I can see it when I walk around the room, because I don't want you Googling stuff. It is closed book. It's going to be mostly short answer and single paragraph questions. So I'm not going to be asking you to write essays. I'm just going to be asking you to just write the answer. I want to know, do you understand key concepts that were presented in the readings and the class lectures? There is no math. There are no calculations, and there is no graphing. I promise you that. You will also have the option of choosing which questions you want to answer. So in other words, I'm going to give you, say, 20 questions, and you pick which 15 questions you want to answer. If you answer more than 15 questions, I'll take your best answers. I know you're going to like this one. I'm going to post some sample questions in the Dropbox in a week. Some of the sample questions will be on the exam. Not all of them, but some of them. So if you have answers to the sample questions and you know what they are, you know that there's a couple of questions on the exam that you're going to be able to answer like that. And last but not least, on the exam, you're going to be responsible for all of the material that was presented in class and contained in the readings through, which means including, October 10. If you have any questions, send me an email, or you can visit during office hours. Thanks. Talk to you guys soon.